Hello friends, welcome to Quickfire Numerical Practice Series for Gate 2021. This video is intended to be used as a ready reckoner for solving numericals, because in this lecture we are not going to look at the rationale behind the formulas being used. Instead, I'll write down the things to remember to solve these kind of numericals. So let's get started. We'll discuss diodes in series for analog electronics, and the things to remember when you encounter a problem like this is that the diode current is equivalent to Is into e raised to the power Vd eta Vt minus 1 for the case of forward bias. And please understand, Vd is the voltage across the diode and Vt is the thermal voltage. Eta will depend upon the material of the diode. For silicon it is going to be 2, for germanium it is going to be 1. So these are the things that you need to commit to your memory. And for reverse bias, the diode current is always equivalent to the saturation current. So Is is the saturation current that may be given in your numerical. So these two formulas are extremely important to solve questions based upon diodes placed in a network in series. For example, if you get this kind of a question where the saturation current for diode 1 is given, saturation current for diode 2 is given, you need to figure out which diode is in forward bias and which diode is in reverse bias. So if you have the positive of the diode connected to the negative terminal, it is in reverse bias, and if you have the positive of the diode connected to the positive of the battery, it is going to be in the forward bias position. So we know that by inspection the diode current 2 will be equivalent to the saturation current of this diode because it is connected in reverse bias, and it becomes super easy to find out the diode current through diode 2 because it is simply the saturation current which was given here. And also because these two diodes are connected in series, so the diode current in 1 will be equivalent to the diode current in 2 because the circuit is in series. So 2 nanoampere will be equivalent to the saturation current of the diode 1 into e raised to the power V naught upon eta is given to be 1 here specifically, so this must be a case of germanium diode. And please understand, the thermal voltage for a silicon diode is 26 millivolt. If it's a silicon diode, eta may explicitly be given as 1 for a specific case, but otherwise if it is not given, you take it as 2 and you take it as 1 for germanium. But anyhow, because eta was given as 1 and the thermal voltage is taken to be 26 millivolt or 25.8 millivolt to be precise, you simply need to use this formula to calculate the voltage across diode 1, which becomes very easy to find once you substitute the values of the diode current through 1 and the saturation current was given, and it becomes 26 millivolt into log of 3. So how cool is that? And then you can apply Kirchhoff's voltage law and see what all voltages are being dropped and what all voltages are being generated. So V2 can now be found out by subtracting V1 from 10. So that's pretty simple. And V1 is already calculated. You need to calculate this using the calculator. This is log to the base natural log. Voltage at diode 2 will be 10 minus Vt log of 3. And that's how you calculate the voltage of the diodes and the currents of the diodes. The current was pretty easy to be found because in series the currents are the same and the saturation current of the diode 2 was equivalent to the current in diode 2 because it was in reverse bias. Now if these two diodes both were placed in forward bias condition, then we could not have inferred it directly. Then you need to remember these two formulas. So for gate preparation, these two formulas are super important. The knowledge of thermal voltage is super important, the knowledge of eta is important, and rest everything is pretty simple. And I hope you liked this quick fire video, and if you did, give it a thumbs up. I'll come up with more such videos every day till we get to Gate 2021. Till then, take care. Bye bye.